Okay, I've clicked recording now, so.
Okay. So yeah, everyone, thanks for coming. I'm Kieran, and I currently work at the Smith Institute, but not too long ago I did a PhD at Warwick, and that's how I know my team. And essentially this is going to be a bit of a general overview of industrial problems in maths and how that's led to some original research, both in PhD and work life afterwards. So I guess stop me at any time for questions, but I'll also finish not after 60 minutes so we can have questions at the end too. Okay, so yeah, currently a senior math consultant at Smith Institute. For that, I was a math consultant, and before that, I was a PhD student for about 4 years, with some internships in between. And my PhD was essentially all about transport, so road networks in the UK, how do you optimize what they're doing, smart motorways, things like that. And my current role is a bit of a mix between energy, so the UK power network, how do you secure the grid, things like that, and fast moving consumer goods. So maybe can't be specific about company, but essentially things you would buy in a shop that have limited shelf lives, things like that, storage, stock of them, things like that. So what do I actually do as a math consultant? Most of my day is spent formulating mathematical problems and implementing them. So these could be anything like someone gives us a bunch of data and asks us a question about it. Someone wants us to forecast or predict something, and there'll be a bit more detail about that later. And also quite a big one is formulating and solving optimization problems. So imagine the UK power grid, you've got N generators, you've got a generation requirement. How do you meet that, subject to how much power you can feed through a transmission line, things like that. Okay, so first 4 years, I realize I've forgotten to set a timer, 1 minute. Okay, first 4 years of sort of my research life were spent doing a PhD that ended up being called data-driven modeling for transportation and smart motorways, something along those lines. And that was also the end of my MSc as well. So on my left, your right, there is a ring road around London called the M25, and a lot of those 4 years was spent taking data from around this ring road and applying various math statistical models to it, publishing papers based on that, and doing some original research. And then the following 2 years, I essentially moved completely out of transport to a bit more diverse applications. Okay, so research I'm going to talk about today. My PhD was sort of split into 4 chapters, but let's just talk about 3 of them. Spatial temporal point process modeling. So the idea here is on a stretch of road, for example this, can you model the occurrence of traffic incidents as they vary in space and time? And explicitly, can we quantify the prevalence of something called secondary incidents, which I'll talk about later on. Anomaly detection. So if I take a stretch of road, in that case, ring road, I give you a data point every minute for, let's say, every location, 500-meter intervals. Can you tell me when there is an incident on the network without human interaction or intervention? And dynamic survival analysis, which is essentially there has been a crash, a breakdown, something like that. Traffic conditions have changed, the jam forms. Can you tell me with some level of confidence how long this will last? More importantly, can you tell me perhaps the 5th and 95th percentiles of the distribution of how long it will last, given where it was, when it happened, things like that. Okay. So actual research points. So spatial temporal point process modeling. Suppose you have a domain in time and space, and the incidents occur in it. And I'm going to call those events or incidents, it's all the same thing. What I'm talking about is car crashes, breakdowns, things that will disrupt traffic flow and create a traffic jam and essentially reduce the efficiency of the road network. And I said to you, okay, I want a model for the occurrence of incidents on this domain. The simplest thing I could do is assume in a given interval of space and time that the number of events, again, is Poisson distributed. So as an example of that, if I just literally write down the Poisson PDF for some parameter, capital lambda.
Oh, sorry.
Okay.
I just was asked to hide the thing, and now that's stopped us sharing. Sorry to interrupt you. So back to PowerPoint. Oh no, we were there. Okay, sorry. Oh no, it's gone. How annoying. Is it going to just stop it again? No. Okay.
So the simplest thing I could do is say the passenger is distributed in some interval of length and time. So the probability that I have little n incidents is literally just the class on PDF with some parameter capital lambda. And what is capital lambda? Well, maybe I say it depends on where you are in the network and what time of day, week, month, year, whatever it is. So I instead write it as lowercase lambda and say we'll write down whatever lambda is here. So yeah, essentially this would fully define a point process, and if I tell you what lambda is, you can simulate it and start drawing some conclusions. And little lambda here, we're going to call the intensity function. So you can think of this as the instantaneous rate of events per unit length per unit time. So then I integrate it over a length and a time to get the Poisson parameter. Okay, so how do I pick lambda here? So this is a practical problem, right? We've all driven on roads. What does the rate of traffic incidents depend on? Well, probably something like the time of day. So rush hour versus not, you get double peaks in traffic flow. So maybe you get double peaks in incidents. Probably day of the week. You know, more people commute on weekdays to work, or at least they did pre-COVID, which was when this was done. Maybe that's not true anymore. Spatial location. So it's just harder to drive on certain locations than others. Maybe long-term trend. So is there an increase or a decrease in the rate of incidents in the UK through time? Are roads getting safer or less safe? And then maybe a whole bunch of extra stuff that we don't know about. But if we start off just by considering this, it seems to at least capture the sensible starting point. So we suppose a form of lambda where we say, I'm going to write down some uniform background intensity. The word background is important in a little bit. And then I'm going to modulate it by a bunch of functions that, you know, one of them is periodic over a day, one is periodic over a week, one is just a long-term trend, and one depends on spatial location. So I'm assuming you can write lambda multiplicatively as a product of terms here. I don't want to fit a four-dimensional function because that turns out to be, well, it introduces a lot more uncertainty in your problem if you try and fit a four-dimensional kernel density estimate versus four one-dimensional estimates. That's sort of a technicality that's not so important in this talk. But I'm going to write these such that each of these functions has average value 1. So if you see them close to 1, they essentially don't, the conditional intensity doesn't fluctuate much with them. Much higher, much lower, you know, increases or decreases the rate of events. So I could write this, somehow determine each of these functions, and I'd have a process I can simulate. But in transport, and a few years ago, there was a serious concern of what was called secondary incidents. So if you imagine there's what we're going to call a primary or a background incident, like a crash or breakdown, a queue forms or a lane closes, and essentially the conditions change, there's the worry that in the short term after this incident or in the wake of this incident, you might have some further incident, like a car driving into the back of a stationary vehicle, and that is much more dangerous than the original incident on average. So how could we incorporate that in the sense that there is nothing here that says, given an event occurred, the intensity of other events may or may not increase? So it turns out this sort of process has a name. It's called a Hawkes process. And we essentially want to say, if we were to fit or extend our approach to this, can we say anything about secondary incidents? Because at the time, we didn't really know how many secondary incidents are there in the UK and what sort of time and length scales do they occur on. So I could alter this intensity function to have all of the terms as before, which I'm going to call the background component. And this is background in the sense that it doesn't depend on the realization of the data. And then I'm going to add another component that's called a triggering component. And this is purely to capture these secondary incidents. So it relies on TI and XI, which is the incidents that have occurred. So, you know, formally we should perhaps write, you know, given XI, TI in the intensity. But we are now explicitly encoding that there are two mechanisms that change the rate of incidence. Things like the time of day, the time of week where you are, and then the actual occurrence of incidents will then change the rate of incidence after in time and upstream in space. If you imagine a queue forms, right, the queue only goes in one direction from the incident backwards, so we wouldn't expect anything to happen forward of the incident. Once you've driven past it, you're good. That's why the sum's one way in time and one way in space. And sort of breaking down what exactly this means, A is in the literature called this triggering rate. Essentially, it's a fraction, so between 0 and 1, and it will tell you what proportion of events in your data are triggered or secondary, or secondary incidents in our case. We sum over all previous events, and we write down two triggering functions, G and H. So these decay in time, and these essentially say how strongly do incidents impact my triggering function, and how long does their influence last. So if the decay is fast, an incident clears quickly. If not, it doesn't. Now, there is still a question of how do you actually determine each of these components? And it turns out the answer is quite technical and way too long to talk about here. So if you actually want the full details, there's several pages of equations in this link. But in short, we gather a data set. So we take a year of accidents along the entire M25, and then we, for each of these, fit a kernel density estimate that tells us, and some non-parametric method that we impose is periodic on a day or periodic on a week, etc. And that reconstructs them without us ever having to specify what they are. But the limitation of doing that is you really want the dimensionality of these functions to be low, which is why we're assuming everything would be completely separable. Okay. So skipping that, assuming you can do it, the results are, so when you actually fit this model, this A parameter, like I said, is a fraction, it tells you the proportion of secondary incidents, and you get about 0.6, 0.7 in all of the models we tried. Essentially, each row of this table is just a different form of the model to check when we include or exclude different features to get anything different. And so the point here is this A is telling you about 6 to 7% of incidents in the data are secondary. So in over a year or slightly over a year, the amount of incidents that happened in a short timescale after initial incidents was about 6 or 7%. So if you were to make some intervention to try and reduce incidents on the M25 or in the UK, you can tackle background incidents, so things just because traffic's dense or whatever, and you can knock off about 97 or 93% of them, or you can tackle secondary incidents, but you're really only aiming for less than 10% of your whole instance set. So it's not clear that actually addressing secondary incidents is the optimal thing to do here. And then we just look at these functions that were part of the intensity before. So, we all know in the UK there's commuting patterns. Typically, peak times is what, like 5 o'clock now. We happen to get a peak at about 4:30. So that's roughly in line with what we'd expect. Similarly, a morning peak's about 8 o'clock on this graph. So sort of a first sense check that the daily background looks about right. The weekly trend is essentially flat. I mean, it's slightly lower on Saturdays, but this seems to suggest that, at least on the domain studied, day of the week doesn't really matter that much. The trend does matter quite a lot. So if you look to about 7 weeks and 28 weeks, there's essentially flat trend for all of it. And then there's a sudden jump and then another flat trend at the end. So something happened about 28 weeks into this study period where the rate of incidence started to quite drastically increase. And that wasn't also known before we did this. Spatially, so obviously we're studying a ring road. So on the right, we have the M25 mapped out with a color that indicates the intensity. And again, intensity here mean the higher values than 1 indicate a higher incident rate. So there are 2 hotspots here which have more than double the average incident rate. One's about 25 kilometers along, one's about 150 kilometers along. Sort of practical relevance of this, if you're going to target somewhere to improve in your network, pick one of these 2 hotspots. And then the really novel thing that we came up with was how to fit this Hawks process to the traffic data. And the output of that are these two functions. So this is the temporal triggering, and this is the spatial triggering. And essentially, we see that the time scale of secondary incidents is about 100 minutes, and the length scale is about 1 kilometer. So essentially, if you have an incident, when do you need to be worried? Well, within the first 100 minutes of it happening and about 1 kilometer downstream, you need to think about doing something preventative, slowing people down, displaying messages, something like that. But beyond that, doesn't really seem to be an issue. So you can sort of relax a little bit as you get further away than 1 kilometer. And this is just a minor point, but you fit some, we've proposed a model, everything looks reasonable enough, but is it statistically valid? So this is essentially just showing you that if you were to take a point process model and ask me, does this represent this data set correctly or well enough to be statistically justified? You can apply something called the inverse time rescaling theorem. And essentially, your residuals in a point process sense should look uniform if you scale them correctly. So this is essentially just saying we've got a uniform CDF on the x-axis, we empirically constructed the data CDF on the y-axis, and if they are about the same, which these black bands give us like a 95% confidence interval around that, then we're happy that it fits the data, and in this case it does. And this is the same thing, but looking at a slightly different measure. But the point is, we propose a model, looks reasonable, looks statistically valid, and we've got some practical conclusions out. So yeah, that's sort of part one, obviously glossing over quite a lot of details. Any questions on point processes? Because we're about to take quite a bit of a diversion away from them.
I have a question.
Mm-hmm.
So you said you're looking at like the first kilometre and the first 100 minutes. So how much is that like realistically done, like on the roads as is? Like is that realistic to do?
So we never specify what time or length scales we're looking at, right? It can be anything up to, I think, 3 days and like 10 kilometers or whatever. These just come out of the data as what the actual timescales are. But at least in the UK, most of the strategic road network is covered with cameras. So you should, in theory, be able to look at a section and look a kilometer back. I don't know if you have enough people to look at the amount of incidents that there are, but in theory, you should be able to do it. Anything else? Okay, so a bit of the detour now to more data sciencey, let's say. Anomaly detection. So same data set, motorways in the UK, 3-ish years of data, let's say. And as we've discovered, incidents occur across the network. They're a major issue because they waste people's time, efficiency, all this sort of thing. There's some associated cost, but in essence, you want fewer of them. And one method to addressing that problem is to identify when they occur. So the current implementation method is people looking at screens. So obviously, limited number of people, lots of screens, it's very inefficient. So how might you detect them, given that I tell you every 500-ish meters, there's a sensor on the UK road network or the motorway network, and there's hundreds of kilometers of road, let's say. We propose something that needs to work in real time. So I don't really care retrospectively 2 hours ago if there was an incident, I care 5 minutes later or whatever. Not require significant labeled data yet. So this essentially is just, there's lots of missing event labels in the UK. If you just look at a time series, label it by when the information system said there wasn't an event. There's clearly lots of issues with missing labels, so we can't exactly rely on them being the ground truth. And we want it to be interpretable because this would only offer advice to some people. So instead of looking at screens, it just says, look at this screen. And they might say, why? Well, I'll tell you why. So how might you do this? Well, there's this concept in traffic called a fundamental diagram. So it's a functional relationship between density and flow on any of these plots. And this is sort of well studied in the traffic literature. You take any motorway in the UK and it will look something like this. And And you might look at this and say, yeah, there's quite a significant amount of scatter, right? I mean, there's one of these trajectories that comes out over here, and if you plot this, this is a sequence of points sequentially in time. So this essentially was a fluctuation away to a high density, low flow regime. So one of the things we were doing quite early on was saying, can we actually quantify how much scatter there is in this plot? Because there's tens of thousands of points laid on top of each other here. So how do you do that? Well, one way would be to make sure everything's stable in time, so make sure the distribution is somewhat stationary, which test in lots of ways, and then construct a probability density estimate from that. So essentially say that this is a representative example of the behavior on a specific section of road. Do something to construct a probability density estimate, let's say kernel density estimation or whatever, and get on the right a 2D distribution. So density and flow is still the axes, but then it's PDF on the Z axis here. And that's obviously very hard to read, but what's perhaps easier to read is if we were to get an analogy of a quantile, but from a 2D distribution. And one way to do that is to write down this function, which is essentially, skip to the next slide. So essentially, I pick some confidence level alpha, I fit a kernel density estimate to the data, which is p hat, and it depends on some matrix sigma. And then I am looking to find a root of this function such that, wow, the mass of my probability distribution cut off at some threshold gives some confidence level. So this is just a quantile in 2D, let's say. And if you do that, same plots we saw before, but these are the 95% quantiles in 2D of those. We're going to call them contours of typical behavior, I think they're referred to as. So on the left, these are also picked because they're examples of things that people talk about in the traffic literature. They just didn't have this way of phrasing it before. So on the left is essentially a very thin linear segment. So for road segments that don't reach critical densities or don't overflow too much, you get something that looks like this all the time. And on the right, you see this sort of extended period of high flow, and that's called a bottleneck flow. So that essentially occurs when a segment of road could, in theory, support higher densities, higher flows, but somewhere upstream there's a bottleneck that limits that. So it doesn't break down, but it just sort of jams at some maximal flow. So what's this got to do with anomaly detection? Well, if I were to give you a univariate distribution and say, tell me where the outliers are, you might do something like just compute the 95th percentile and give me all the numbers above that, something like that. And it's not too different to giving you a bivariate distribution, computing one of these contours, and then telling me where points are outside of it. And the data we get is also sequential in time. We get a point every minute. So suppose we compute one of these regions and we look minute to minute of the density flow data that comes in, and we track these fluctuations from these regions, and we say that could be a proxy for an incident alert. So something to tell a human, look at this area because something's abnormal here. And as an example, so this is a different section of road, but exactly the same procedure. And then in red, we've colored a stretch of density flow data minute by minute, where you see one of these fluctuations and then return. And essentially the point is show a human this, and they say, okay, for some reason, the flow is dropping here, the density is increasing, well, that is a traffic jam. And then do whatever they want about that, change some speed limits, go out and fix a problem, something like that. Now, if I show you the exact same plots, but show you travel time on the y-axis instead of density and flow, I've colored the travel time by the events raised by the system. So whenever there is a fluctuation outside one of these contours, it's got a non-dark blue color, and red is a more extreme fluctuation. And these sort of fluctuations in density flow space correlate quite well with travel time spikes, which are, of course, things people care about, right? People want to get to where they're going in the minimal time they can, legally and whatnot. So we haven't actually modeled travel time ever. We haven't done any validation of a really complex time series model here, we've just essentially constructed a 2D quantile of some data, and then it happens to have reconstructed these travel time spikes, which makes sense because high density, low flow, it's all related. But the nice thing about this is we don't actually need any labels to do this. We've just constructed a threshold distribution. And also we don't need any GPUs. So finding if a point is inside an arbitrary shape is called a pointing polygon problem, and there are efficient ways to do this without GPUs. So you could in theory do this at every single roadside unit. I said there's a sensor every 500 meters. We don't really have any computational demand here that's unreasonable. So how do you know this is any good? Well, there's sort of 3 performance metrics people think about when they're doing this sort of problem. And now I said before that the flags weren't reliable, so you have to take all of this with a bit of grain of salt because we're validating as best we can, but we know that the original source isn't perfect. So detection rate is, I have these incidents labeled in my data set. Someone looked at this and said, yeah, there's a crash there. How many of them were actually flagged by this method? False alarm rate is how often did we raise a flag when there was actually no problem at all? And then mean time to detect is, given there was a flag in the data, how long did it take us to flag it? And again, these flags, there are some of them missing, so your detection rate's a bit uncertain, and your false alarm rate's a bit uncertain. And we don't actually know the exact time an event started, so our mean time to detect is also uncertain. But this is the current state of traffic modeling, so you can't really do much better. And we compare to some reference methodology, the standard normal deviate. It's just something that's very simple to use and widespread in traffic. And the point is, if you do this approach, which is not all that computationally demanding, you see that statistically, no real change in detection rate, a significantly better false alarm rate, and no real change in mean time to detect. So we've not got worse in 2 categories, but we've got better in 1. And the point is, someone said to me, well, why does this methodology work? And imagine I gave you a univariate distribution, and I said to you, tell me the outliers. One thing you might do is just look at the 95th percentile and pressure above that. Or you might say, I'm going to take the mean or the median, you compute some measure of spread, and then say something like, if you're, I don't know, 1.5 times the interquartile range above the mean, then I'll flag. That's what a box plot does in any standard software. The issue is, if your data is bimodal, and you do that, your mean is somewhere in the middle of the 2 modes, your variance is huge, so you're either never going to flag or always going to flag, right? Because you can't well characterize a bimodal distribution by its mean and variance. And these are just 2 real examples of bins in the data where this happens. So for whatever reason, the traffic speed on a given section of road is bimodal in those 2 places. If you do the same thing, but for the method we propose, these 2 modes move around in density flow space, but they don't move out of typical behavior here. So you can see essentially this would be one mode, which would be low density, high flow. This would be another mode, which would be high density, high flow. But they're both captured in what is normal in 2 dimensions, but not what is normal in 1 dimension. So that's like a simple example of why this method actually works. Any questions on anomaly detection before we move off traffic?
Has there been any uptake of this method?
So I had a chat with National Highways. Well, okay, when we did this, they were called Highways England, but now we're called National Highways, maybe 3 months ago. And there was some talk about it, but it's not in use yet anywhere. No, I think depends.
Sounds like there's some significant interest though. That there might be. These things don't take 5 minutes; they do take several years. Don't they?
Oh yeah, exactly.
So,
yeah.
So I'm working on this project, strangely, in the next couple of months. I think initiatives help National Highways detect incidents.
Okay.
There you go.
Fascinating. I want to see what you've done more.
This is
And there's been a bit of history
strange.
to that as well, so other consultants
Just timed out, I guess.
Yeah.
I'm building on that.
Oh, excellent. Okay. That sounds really interesting.
Oh, sound.
I did a master's project on traffic flows, so you're all right.
So I've put more in the past on the speed flow curve, which is also two-dimensional.
Yeah. I suppose you could, you just need 2 dimensions, right? It could be speed flow, it could be density flow. Doesn't matter too much what you
It's in
pick.
the middle of that curve.
Yeah.
That's what it is.
Making a noise.
What's going on now?
You get to text it.
Amazing.
Here we go. Sorry.
Sorry about that.
Am I still on Zoom?
Yeah, I think it was literally just a screenshotting there. It's still all good.
Okay. So, moving on from that, it may seem a bit jarring that I'm switching between topics here, but
Oh, sorry, you've got a couple of questions on the
Oh,
chat
okay.
in that section.
Yeah.
So, what currently happens with the data the sensors every 500 meters are collecting?
so at least when I was doing my PhD, it was all put into a system called NTIS, which is the National Traffic Information Service. You could, in theory, just register for an account, go pull it, and start doing whatever you want with it. I don't know if that's still publicly accessible or not. I mean, do you know?
I don't think it's publicly.
Okay, so yeah, maybe now you need some other way to access it. But I'm sure it's being stored somewhere still.
I think it's also used, is it not? It's not used to with the smart motorways to help guide the changes in speed limits and things like that. That's what it's for, isn't it, originally?
Yeah, so there's 2 slightly different systems. One of them is called Motorway Incident Detection Automated Signaling, which sets the caution cue ahead signs and things like that.
Yeah.
And then there's sort of a separate repository of extra speed flow travel time data, which I'm not sure how widely used that is still in practice.
And there's just someone saying, what is the meaning of the red points on the 2 anomaly detection graphs?
So these would be points we would flag as anomalies in this example. So we take the black is close enough to typical that we wouldn't flag to a human, but the red is sufficiently far away that we would. Okay. So yeah, it may feel a bit jarring. I'm swapping between topics quite a lot, but this is sort of a rule of thumb of things I've done over the past 4 years that, it's all been data science / mathsy, but wildly varying applications. So energy, we all use a lot of energy. You'll hear a lot of horror stories about energy in the news, and the UK energy grid is changing a lot. So we have renewable generation. Perhaps in 2050 we'll have a net zero grid. We've got new technologies like batteries and electric vehicles coming in that can either supply the grid or take demand from it. And balancing the grid is becoming increasingly complex. So 30, 40 years ago, it was nowhere near as challenging as it is now. So when I say balancing the grid, what I specifically mean is ensuring that supply and demand are always in balance on whatever timescale you're interested in. But it could also mean making sure system frequency remains at whatever the ideal amount is. So to balance the grid, we use lots of things, but essentially you need to make sure that your generation or your supply meets the demand. The issue is you don't know what your demand is going to be in the future, right? How many people are going to boil their kettle or whatever. So you forecast what the demand is going to be, and you have a set of generators, wind turbines, solar plants, coal plants, whatever, that are going to provide some generation. And based on those forecasts, you can tell them to do things. A day out, 4 hours out, whatever. But all of these forecasts, both of the actual demand that people are going to place on the system and what the generators are going to output, have associated uncertainties. And these are not Gaussian distributed, et cetera, et cetera. So we need to protect against this uncertainty by holding some quantity called a reserve. And you can think of reserve as spare capacity. If the demand is a lot higher than I thought it was going to be, I've got some spare capacity and I can use it. If it's not, I'll just not use it. So how much reserve do I need to hold? Well, ideally, you want to hold as little as possible because it costs you money to hold excess generation. However, the less reserve you hold, the more at risk you are of not having enough generation if your forecast error is wrong or if your forecast error is large. So there's some balancing act here between how much you're willing to pay and how risky you want to be. and you have to trade those two things off. There's no way around this. But assuming you can tell me what your risk appetite is, what actually impacts the amount of reserve you're going to need. Nowadays we have wind turbines and solar generators, so the weather, maybe my wind forecast was a little bit wrong, so my wind turbine can't generate what I thought it was going to. Time, so plants want to do different things at different time of day. Generator reliability, so when it's very cold, certain coal plants break down, things like that, and lots of other things which may or may not have a significant impact. So when I say we, Smith Institute and National Grid are currently doing a project called Dynamic Reserve Setting. And the idea is to dynamically recommend how much reserve you need to hold based on things like weather forecasts, well, a lot of it's based on weather forecasts, but also things like events, times of day, things like that. And in essence, this is a forecasting/data science project that we break down into collecting data from the UK energy grid and every single unit's forecasts and the generation requirements, computing these forecast errors, and it's not quite an error in the sense that it's just actual minus forecast. It's a bit more complicated than that. Building models to satisfy some risk appetite. So, maybe they say we want one incident where we have insufficient reserve per X time. Breaking these model results into contributions from each feature. So essentially explaining why we are recommended a given amount of reserve, and then presenting these breakdowns to domain experts, because the people actually buying and selling reserve, are sitting in a room somewhere in National Grid control, phoning up generators, working out what they need, and to get them to trust the 4 preceding boxes is a fairly big part of this project. So the model it's machine learning. We use a tree-based model with a variable risk appetite to essentially model quantiles of this distribution of the distribution of forecast errors, conditioned on all sorts of weather and time properties. But a big part of this project, and the main thing I'm going to talk about, is interpretability. So suppose I give you an arbitrary machine learning model, neural network, tree, whatever, doesn't really matter. How do you make those things interpretable to humans? And from all my experience, if you don't have an interpretable model, your machine learning solution almost certainly not get used. So one way to derive explanations of what our machine learning model is doing is to compute something called Shapley values. So these actually have nothing to do with machine learning. They arose in game theory quite a long time ago. And Shapley is the name of the guy who came up with them in game theory. And essentially he said, suppose I have some value function in game theory or some payoff. I can break that down into the sum of what he calls Shap values, so these phi's. And if I have m players, the total payoff is some baseline plus the contribution for each player. And then in 2017, I believe, some people came along and said, this is not all that different to saying I've got a machine learning model that has a prediction, and I've got m features, and I want to break it down into a baseline and plus the contribution from each feature. Now, this is fairly widely adopted now in terms of machine learning explainability, but there are other methods that exist. So how do you work out a Shap value? I suppose at this point, we've got all of our data, we've trained a model, we can generate predictions, and now we just want to generate explanations. So how do you work out Shap values? Well, this is what Shapley wrote down. This is formulation of them. Bit of context. So phi I, for a single feature I, the Shap value, which is its contribution in an additive manner, is the sum over all possible feature subsets, that S, we're going to call them, some normalization constant, times essentially the difference in model output, if my model is F, of including feature yi and excluding feature yi. So this is not at all obvious why this is true, but imagine I have an empty feature set and I add features at random. At some point, I add the feature of interest, okay? And suppose S is the set just before I add my feature of interest. how many ways could I have formulated S? Well, that's factorial. And then add feature of interest in. How many ways can I add the remaining features in? That's this guy. And then how many possible subsets do I have overall of features? Well, if F is my feature set, it's mod F factorial. That's where the normalization constant comes from. And then the idea here is essentially to weight the contribution, well, weight the model output when I include it and exclude a feature. With the idea being that if I include a feature, the model output changes. If it changes a lot, then that's got a significant impact. If it doesn't really change at all, it's got no impact. But there is an issue with computing. Well, okay, there's two issues. Does anybody see two issues with actually evaluating this formula? The first is that I'm summing over all possible subsets, which there are an exponential number of. So I've got to sum over an enormous number of terms, and the larger my model gets, the worse this gets. And also, I've got an arbitrary model, a neural network or whatever. How do I evaluate this model excluding a given feature? Right? You can't just sub in nothing. Subbing in 0 has a meaning, so you can't just sub in a missing feature to an arbitrary machine learning model. So in actual fact, there's quite a few extra steps in computing Shat values. The first is to approximate this term with an expectation. So you say, I'm going to fix certain features, and then the rest I'm going to resample and take an expectation over that, and then say that is my approximation of what the model would do if I didn't include this feature. But that itself then is multiple evaluations of the model. And because I don't really want to sum over all possible subsets, there are various computational tricks to speed that up. So it's provably possible to show that you can formulate Shat values as a linear regression problem where you just have a fairly large design matrix, and there are ways to then say which rows you can throw away to reduce the dimensionality and speed it up. And that was what brought them into the machine learning sort of area, in that you could do these tricks to speed it up and actually get something to compute in a sensible amount of time. So this is an example, a real example of a reserve we recommend split up into its contributions, where the contributions are Shat values. So blue here means a decrease, red here means an increase. And we always have some baseline, which you can think of as the average model output over the entire data set, or the entire training set. So here, on average, we would recommend 355 megawatts of reserve. For this specific data point, we recommend 3994 megawatts. How do we get from this average to this specific data point? Well, bank holiday and this feature, it's not important what it is, didn't change it at all. The fact it's a Tuesday added 4.3 megawatts. The fact that the national demand was, this value took 15 megawatts off. The fact it's June took 87 megawatts off, etc., until we get to final model output. So this is why we've got an additive break. We can just add these numbers to get to the end. And this essentially is when we show our predictions to people who are buying reserve, we don't just show them a number, we show them this breakdown, and they can then see, okay, well, the wind speed, I know something about that. I know I don't trust my wind forecast because I can look out the window and I know it's significantly different to what my weather forecast is saying. And so this is how we sort of are building trust in this model of actually working, as well as obviously the validation of all your standard validation metrics, drift through time, all that sort of stuff. Big part of that is explainability on top. And this is just an example of the model in use, but its actual outputs. So here we've got the series we are modeling in grey points, and then we're predicting some upper threshold of this, so some level of risk. In this case, perhaps the 99th quantile and 99th quantile, with the idea being you really don't want to run out of reserve very often, which is why we're aiming for quite high quantiles. And this is just an example through time of two different quantiles. You can do the y-axis here is reserve, the x-axis is time. Okay, maybe I've got a little bit of time to talk about this. So that's one. Well, okay. Are there any questions on dynamic reserve setting before I move on from that? Yeah.
Yeah. So the previous slide, you don't seem to show any uncertainty, but there must be uncertainty in those estimates.
In the Shat value estimates.
Well, in the estimates of how much energy reserve you require.
Mm-hmm. So there's in a sense, we're aiming for a quantile, but you're saying that the estimate of that quantile is also uncertain.
Yeah.
Yeah. I think in terms of the explanations of uncertainty, outstanding research problem.
Yeah.
In terms of our estimates, we actually update the model through time.
Yeah.
So aiming for the same time period, we would make predictions at a given time, and then we get some more information and make a new prediction. Then we've got a set of predictions that people can look at and say, well, okay, I know the weather forecast got better or worse or whatever. And it's sort of human judgment to say, well, okay, I've got this range. Now, what am I going to choose to do? And I'll be somewhere close to the risk I want to be.
How far in advance do you forecast?
In this example, at 11 a.m. on a given day, we would forecast from 5 a.m. on the next day to 5 a.m. the day after. Because actually buying reserve and getting, plants spinning and stuff like that, it takes time. Anything else? Okay. So that is very much a data science project, right? It's explainable AI. Bit of a game change here is optimization. This is the only slide I have on this because this could be a massive talk in itself. But in there, in the last few slides at least, we were talking about day ahead, let's say. Here now we're thinking about, I'm sitting in the control room, I'm actually moving generators around, and in the next hour, 2 hours, 4 hours, I need to make sure that I have enough generation to meet my demand. And I can't be over or under in this case, or my system frequency will start changing. So one of the things we've done is generate something called a modernized optimization algorithm, essentially solving the optimization problem of how should I move each of my generators up or down, what their output's going to be, to match my demand prediction through time, subject to constraints. For example, you can only send so much energy through a wire, that overheats, things like that, as well as plants can only ramp up or down sufficiently fast, as well as wind turbines can't generate more than the wind allows them to, things like that. And then we iteratively solve this again and again to essentially, on the really short time scale, give instructions of how should I move my units to actually balance this grid whilst occurring minimal cost. And when I was saying earlier about the amount of complexity in the grid's increasing a lot, a long time ago, this might not have been such a hard problem because the types of units you had were very similar. They were all just big coal plants, and the number of them you had was much smaller. Whereas now, it's not just a linear program to solve this, it turns into a mixed integer programming for all sorts of specific application reasons. But this is another thing we've worked on in the past with National Grid. So this title of this talk was Lessons Learned, so I thought I should put some lessons at the end of it. So in practice, we do some applied maths problem, we come up with some research paper or tool for people to use or whatever. And oftentimes, I think, when we're setting out on this problem, what is actually going to make a solution useful in this scenario, right? Is it my model performs optimally on some error metric? Like I was showing with the incident detection, is it that has a time to detect of 0 or 1 minute or whatever? Or is it that the model is interpretable and I lose something on my error metric? Is it that it has certain compute requirements? So, if I need a GPU farm and I get a 5% better performance and an uninterpretable model, do I just need to ditch the model and do something else? Is it that the data requirements are going to give us something extremely complicated to implement? For example, if I need to set up huge pipelines that clean data and pull it from 10 different sources, can I actually rely on all those sources actually surviving for the next 3, 5, 10 years? Or will it just become obsolete? Another one is data processing is often a huge task. So the quality of data you get given in practical applications varies wildly. And very often there are some non-trivial issues, missing values that aren't missing at random, or periods where something changed but it's not recorded anywhere, so you have to work out why exactly and build that into your model. Uncertainties about recorded values, and perhaps more technically, but just oftentimes, how do you even store this amount of data? If I give you 1 million images, what are you going to do? Store them all as something on your laptop or set up some of the files. You know, there's graph databases to use. There's how do I index all of my things correctly? Do I want to use Parquet files or whatnot? But I remember a long time ago, you save everything as a CSV and be done with it. Yeah, that very quickly becomes redundant in practice. And I think this is the last slide. Keeping up to date with methods in the literature. Very often you get, well, people come to us with problems that are slightly different to a typical problem. Very rarely does someone come along with a problem and you say, oh yeah, classic machine learning, let's use this method, do that. And there's something unique about it, a constraint, something on the data that means you can't just take a package off the internet and apply it. There's always something intricate about it. And understanding how to overcome these very specific points, I found pretty useful just to keep reading papers on what's new in data science, machine learning, point processes, whatever. And understanding the underpinnings of models. So, I think there's a bit of a danger when data science becomes more widely implemented that people will just use a model, and then the next time they see a problem, the idea is when you've got a hammer, everything looks like a nail. Maybe when you've got a neural network, everything looks like a neural network problem. And I really do think there's a bit of a danger that people are just going to have used the model, it worked in the past, and then just apply it without thinking. And definitely we want to be avoiding that as responsible mathematicians and statisticians and whatnot. I guess the last point is, someone comes to you with a problem. What are you actually aiming to do? Give them predictions of something, advice on what they should do, automation, insights into their data, validation or assurance that what they're doing or what they've got works. And based on this answer, what I would do would vary wildly. If someone wants a fully automated system, what I would consider doing is vastly different to someone who just wants some advice that a human will then look at and do something on. And I think understanding that these are wildly different problems is quite important going forward, especially when we start talking about machine learning, nonlinear models, black boxes, and whatnot. I mean, obviously, always end with a reference slide, but if anybody actually wants these, just email me and I'll send you some links. Yeah. Any questions from that fairly quick tour of the past 6 years of my life?
Can I ask about the ways and the times of how you include the problem owners in the development of the solutions?
So typically, it's several iterations of speaking to some domain expert, partially to understand what data they've got, partially to understand what solution they want, because often people can't exactly define what they want, right? They can say they've got a problem, but what exactly do they want? Is it better predictions? Is it just to understand one thing better? And then when that's clarified, start implementing things and have lots and lots of interactions as we go, because I mean, you can quite easily diverge massively and people don't get quite what they expected, even if at first they thought they understood, especially when you're talking about some really obscure, complicated problem or method, right? It's very easy to sort of get lost in the weeds and start viewing different things. Anything else?
Maybe related to that, how do you, I guess, estimate what it's possible for you to do given a problem that someone just come to you and said, I've got this data on traffic flows and I want to understand if I can do this. I assume you can't just instantly say, yes, it's possible to do this. What's your process doing, whether you can actually do that thing?
So more recently, we do start with these sort of scoping phases where we say, okay, in the first month, 3 months or whatever, we'll look at your data, establish exactly what problem you want to solve or what problems you can solve and not. I think a lot of the times people come to us, they don't want the world. They sort of understand that there are limitations to what we can do. But yeah, there is normally a month or two where you're really defining a problem as part of the work.
Into bang the uncertainty drum again. So it's really important that if somebody is relying on a mathematical statistical problem, a model, that they understand what the underlying assumptions are and what those assumptions lean in terms of what they can rely on,
Mhm.
and also where are the sources of information, sources of uncertainty, and what that will do to the range of suggestions or supports that they are given. So how do you find that? Do you find visualizing uncertainty easy? Do you find it? Do you find clients think, well, if you've got this much uncertainty, you don't know what you're doing, do you? Or how does that work out in practice and what you do?
So well, I guess the simplest way is to say, we've got these are the inputs to the model or whatever. So, it's not considering any of X, Y, or Z as the first thing. But the other thing is when you look at these additive breakdowns, if we do use this as an example, some people might have preconceptions about different things that will appear as features in these models. So if national demand appears, suppose this was a forecast, they might say, oh, I don't trust the national demand forecast on a Tuesday, or something like that. So it's sort of clear to them when you break it down into these methods that, if national demand is huge contribution and they know they don't trust it on a Tuesday or whatever, it's a bit more information on them as to what they can do.
Sure. It doesn't quantify the uncertainty in how much reserve there should be set.
It doesn't know.
It just says this is less reliable than usual, or than I would like it to be.
Yeah, I suppose that there are multiple methods in which people decide what reserve comes up.
Yeah.
And so pointing out that a particular method, this is one that you can trust or not trust at this time point. Yeah.
Richard's got a question online that says, does the power reserve data go down to the level of local electricity substations or even to the level of individual household smart meters?
Not smart meters for us. Someone might have that data, but that's not what we're working with. Essentially, we're looking at any unit that is on the balancing mechanism in the UK. So, wind turbines, large solar plants, coal plants, anything of that type would be included in it. Now, there will be forecasts of things called embedded. So embedded wind load factor here is a feature you can see. Embedded generation is stuff National Grid don't control. It's, an example is you stick a solar panel on your house. They can't do much about that. It's just there and the sun may or may not shine. Whereas they can adjust what a unit in the balancing mechanism is doing.
I think the point there is the substation's part of distribution, not part of generation, isn't it?
Yeah, so there are distribution network operators like SSEN is one of them. They are in charge of the actual physical cabling and things like that. That all this stuff runs through.
Going back to your point about people, using the hammer they developed in their PhD to crack any nut that happens to be passing. So this is exactly the reason why the IMA and the RSS and others got together and defined data science standards. And so you can register now as a data scientist, you can register that you've reached a certain level of competence, and the idea being that once you're accredited in this way, then the client knows a bit what you're getting. So is there take up in Smith or in other institutes that you know of that are doing this kind of this work to go forward with that? It's very new. Probably wouldn't have done it yet, but
This is the first I've heard of this. When did it come about?
I think the first people were
About a year.
about a year ago or 6 months ago even. Their assessment was passed. So there was but it's data science standards. All the mathematical sciences professional bodies have got together and define these standards. So me and my unit haven't done it yet. I have to say it's on plan, but because we're commerce facing, we think this is going to be important because there are so many travels. It's like check and trade, but for statisticians.
I definitely agree it's a good idea to have these standards, yeah.
Yeah, because we end up on the receiving end of so much of other people's bad stuff, don't we?
Yeah. I mean, yeah, sometimes projects can be fixing things that are already there that don't work for a specific reason, and then you look at them and go, okay, it's because this is not fundamentally a problem that should be solved in this way.
Going all the way back to the distribution of incidents, what else did you consider? Were you definitely going for Poisson, and did you consider any of the modulation functions?
So, in terms of the contributions, We looked at adding more of these periodic ones in, so maybe things like periodic 2 weeks or whatnot.
Yeah.
And we thought maybe factories have working patterns that fit it, but everything we tried looked flat. So the ones I showed you were the ones that essentially were insightful in some way.
Even the weekday one was quite flat.
Yeah, and that was like the limit of, okay, anything flatter than that is sort of looking a bit redundant. Part of the issue with those types of models, with Hawkes processes in general, is if you were to fit a standard statistical model, you might work out information criteria or whatever, and you'd know you could penalize model size, right? That metric isn't defined for Hawkes processes, so you have to look at just log likelihood, which will almost always get better as you add more terms, right? So it's sort of more of a manual judgment of when you should stop.
Yeah.
I don't know if anybody's done any sort of advancement on model selection for Hawkes processes since I finished, but at the time it was very much people use it for like earthquakes and things, and they just write down an equation and go with it, and then it's valid at the end, it's all good. Was sort of the practice.
We've got one more online that says, after you've spent time and effort defining a problem, how often do you find that the solution becomes obvious or easy to generate?
I'd very rarely say that we solve a problem where the solution's obvious. There might be differing difficulties of problems. Some things you look at and say, okay, this is a multi-year, huge effort, or this is maybe a 3-month thing. But I think when people come to us with these problems, they have tried to think about themselves and realize something about it is hard, whether that be the entire formulation or just one specific forecast or aspect of it. So I don't think I've ever got a problem where I'm like, oh wow, easy, a week and we're done, sort of thing. Yeah.
Do you have any advice for anybody who's listening in who is a PhD student, not sure whether to stay in academia or go into industry? What would you say is the easy and the hard bit about going into industry?
I think, well, during the in the last year of my PhD, I did do 2 internships, after which I was like, okay, I'm joining industry rather than being an academic. I think the large difference is, well, it depends what company you join as well, right? There could be companies out there that are sort of solve run-of-the-mill problems, your classic, we do this one thing really well, and we're going to just do that for lots of different people, or ones that look at a complete range of problems, and maybe you don't know how to solve them, and it's all innovation style work and whatnot. And a lot of what we do is in the latter half. People don't know how to solve these problems. There isn't a method out there, so we work out what to do. And that appealed to me, and it's sort of halfway between research and industry. We're not implementing things that everyone knows how to do on our data sets. We're sort of half discovering new ways to do stuff and half saying, well, okay, how do you merge that with industry? So for me, I guess it's a pretty bad example that I went in a split between the two. But I would say, yeah, do some level of internship, get a feel for it, and then decide, what do you care about? Do you care about practical problems, or do you care about the underlying methods, and that's it, and go from there? I mean, there's all of the things with academia, right, like race to publish papers and whatnot, but I think it's more of a personal choice.
Sure. I just wondered what your, having done that transition, I thought it might be useful for people to hear, that. So. Was there anything particularly difficult about the culture? I know yours is a research institute, so you are still doing research and that kind of thing, creating bespoke problems. But academia has a very particular culture which is not found anywhere else, as far as I can see, in the workplace. Is there something that's particularly appealing or particularly different? Or
I think maybe not everybody would agree with me, but I find it's a little bit more relaxed than academia. I find in academia people would just work in crazy hours to publish stuff, and I finish at 5:30 and that's it until the next day or whatever, right? And after finishing my PhD, I was like, oh, this is new, isn't it? But I'm a big fan of this much more, I guess, better work-life balance than before. So other differences, I think in academia you can sort of pick your own problems within your funding grant space, whereas we have to solve a problem that dynamically sets reserve. We work out how to do it and exactly how that should be done, but fundamentally we the thing we're aiming for is fixed, and some people may or may not like those constraints.
So different debate, but my son has just jumped from academia into industry, and he says one of the key things for him is that when he's on annual leave, somebody else does his tasks. And that's a big difference, because in academia, they just pile up waiting for you when you come back. You know, there might be a few very specific things that somebody has to do for you, but generally, all your emails are waiting for you, your research doesn't get done, your teaching doesn't get done if you're away, if you're sick, or whatever. So it's all there waiting for you. He really liked that being much more part of the team, effort, so that if you are away, somebody else will get that job done. You'll come back to it and make your contribution somewhere else.
Yeah, that's what I didn't think of that, but early career research for sure is somewhat isolating, right? In that you are solving your problem and you maybe have a supervisor or a research group, but 99% of what you do is you thinking about stuff. And at least in industry, we've never got to the point of where just one person is working on a project and that's that. It's a bit too risky to actually have as a working pattern.
I'm going to stop recording now.